All right, hello everyone. Welcome to the 2021 DAFoam Workshop. And my name is Ping, and I'm the organizer of this workshop. So first of all, I'm very glad to see some familiar faces and names. And I'm very glad to meet some of you for the first time. And I would like to say thank you to all of you for being here and for your interest in using DAFoam. So this workshop will have 3 sections. It will from the 9 a.m. Eastern time to the 12 p.m. to the noon. And each section we will do about 50 minutes lectures, presentation, and discussion. After that, we will have a 10 minutes break between 2 sections. And this will be the first section of this workshop. Let me go to the next page. This workshop has 4 main objectives. After this workshop, you should be able to first get familiar with the high fidelity design optimization framework called MACH-Aero. So that's the first objective. The second objective is that you should be able to get describe the details in the OpenFOAM and DAFoam configuration files, such as this control dict, FV skins, or run script or py. The third objective is that you should be able to run aerodynamic optimization with DAFoam. In this workshop, we will have some hands-on examples. We're going to go over some cases together. So the last objective is that you should be able to adjust the configuration files if you want to run a new case. Could be a new airfoil shape or could be a new flight condition. So these are the 4 main objectives of this workshop. Before I start, I would like to mention a few notes. First, based on the feedback when you sign up, and we assume that you are familiar with the basic concept of CFD. So, which means that in this workshop, we are now going to talk about what is initial and boundary conditions and what's a finite volume method. We assume that you are already familiar with that. And also we assume that you are familiar with the basic Linux commands, such as how to create, how to modify and save files, because we're going to use those commands for the hands-on examples. So also I want to emphasize that this workshop focuses on how to use DAFoam. We are not going to talk about how to develop DAFoam. And then this workshop has hands-on examples, and I'm going to run some cases. And then later on, I have some instructions on how do you download the so-called DAFoam Docker image, and then how to run a case. And this workshop is supposed to be interactive. So if you have any questions, please feel free to stop me at any time and ask, or you can type in the chat. So for some reason, if I cannot see the chat, please remind me. All right, by the way, this, as you probably know, that this meeting is being recorded. After the workshop, I'm going to post it online. All the materials are open source and available at this address, including this slide and all the video recording. After this is done, I'm going to post online. All right. Okay, so today we're going to have 4 main topics: DAFoN Introduction, MACH-Aero Framework, and airfoil and wing aerodynamic optimization. So of course, DAFoN's capabilities includes some other applications, but today we are going to focus on how to run airfoil and wing aerodynamic optimizations. Okay, DAFoN introduction. So what is DAFoN? DAFoN is short for discrete adjoint with OpenFOAM. So you can see the DAFoN here. So I'm going to explain what's OpenFOAM if I'm not very familiar with it later, and actually in the next slide. But basically, you can use DAFoN to do 4 things. First, if you want, you can use DAFoN to compute the so-called sensitivities for a large number of design variables. If you are interested in using the so-called, sensitivity map in your design, then you can use DAFoN to compute the sensitivity map. Also, the second thing you can use DAFoN to do is that you can couple with a gradient-based optimization algorithm to do design optimization. The second application is the main focus of this workshop. So of course, you can also use DAFoN to run OpenFOAM flow simulations to generate CFD samples to cover your design space. For example, if you want to do some surrogate-based design optimization, you can use DAFoam to do that because we have a Python interface that allows you to change the design and explore the design space very easily. Of course, you can also use DAFoam to easily access the residuals, indexings, for example, file input and output operations in OpenFOAM. All right. So as I mentioned, DAFoam is just implements the discrete adjoint method to compute derivatives for OpenFOAM. But what is OpenFOAM? OpenFOAM is an open source field operation and manipulation software. And it's written in C++. It has a lot of libraries to essentially facilitate numerical operations of field variables, such as, for example, solve some linear equations or compute partial derivatives in your for PDE. Building on these libraries, OpenFOAM also has more than 80 solvers. When we say OpenFOAM solvers, we mean that some binary executives, or you can think of apps, to actually solve the flow and solve the PDEs. For fluid mechanics problem, it will be the Navier-Stokes equation. But for example, for other problems, it will solve a different set of PDEs. And these are the actual thing we run when we use OpenFOAM. But later on, you will see that in DAFoam, we never use these binary executives. We are going to compile everything into library. I'm going to elaborate on that later. And also OpenFOAM has a wide range of utilities for post-processing and pre-processing, such as generating mesh and checking mesh quality. So OpenFOAM is a very popular open source CFD package. That's why we want to enable the discrete adjoint capability and then use it for design optimization. All right, next. As I mentioned, the DAFoam and just is based on OpenFOAM. And one thing I want to mention that we only support a specific version of OpenFOAM, which is the ESI branch version 1812. Although OpenFOAM does have 3 main branches, like ESI branch and OpenFOAM Foundation branch, extend projects, but we only support this branch with a specific version, although their latest version is 2012. We do not support 2012 yet at this moment, but it should be straightforward to extend that. But it will be tricky to extend for other branches. Just keep that in mind. Next. Okay, here is a little bit history of DAFoam. So this project started by my colleagues in the MDO lab at the University of Michigan in 2014. And then in 2016, I joined MDO lab and I took over the project. After that, we managed to publish a few papers. And then in 2019, we make this code open source. And then in 2020, we extend the capability for multiple solvers. We also upgrade to version 2. And this workshop was based on version 2, which is a major update that basically get rid of all the file I/O and wrap everything into libraries, which means the way we run OpenFOAM in DAFoam is very different from the original OpenFOAM. Later on, I will elaborate on that. And very recently, like December last year, we add the Jacobian-free adjoint capability with automatic differentiation. And then we use the CODIPAD and MEDIPAD to differentiate OpenFOAM. And this allows us to get adjoint derivative with very accurate, like machine precision accurate. All right. That was a very brief introduction to DAFoam. And now I'm going to go to the next topic. It's MACH-Aero Framework. As I mentioned, DAFoam itself does not do optimization. It just computes derivatives. We need a lot of other components or modules to actually do optimization. And the framework we use to do optimization is called MACH-Aero. So what's MACH-Aero? It's a high fidelity design optimization framework developed by the MDO lab at Michigan. And by the way, this framework is open source at this address. And this diagram basically explains how does that work. For some of you, maybe you are very familiar with this. For if you are not very familiar with it, I do want to spend some time to talk about some details of this framework. If you have any questions, feel free to ask. So first, let's talk about how to read these diagrams. You can see a lot of blocks here, the diagonal blocks, these colors. they are the so-called modules or components. So you can think of each module is a code. So DAFoam is module number 6, adjoint solver to compute the gradients. OpenFOAM will be the module 5, flow solver. But of course, we need many other modules. These are the diagonal blocks. So you can see they are in the off diagonal box, we have some white blocks. They are basically the data transfer. So a module will receive data in the vertical directions and do some computation, do some manipulation of your data, and output the data in the horizontal direction. So that's how we read this. Okay, so this framework will start with the number 1 all the way goes to, I think, it will goes to number 7 and loop this. So how does that work is that you will start with the first module, which we called the pre-processing. This module will do 2 things. It will generate the mesh. It will also generate the FFD points. What is FFD points? I will explain that later. Basically, there are some control points we manipulate, we change in the design optimization. We use this control points coordinate displacement as the design variable. So in the pre-processing, you only need to do it once. You generate the mesh once, generate the FFD point once. After that, you go to this optimizer, the second module. And this module will receive a couple of things. First, it will receive the baseline design, essentially the original coordinates of your FFD points. Their displacement will be all 0. So, and as well as some function values from the previous iteration, because there's the first iteration, we will not receive any function values. And the output of this optimizer is the update FFD point displacement, which essentially the design variables. But of course, for the baseline design, as I mentioned, the displacement will be all 0. We are going to use the original FFD point. Those control points will not move. Based on this, we go to the next module, which is number 3, geometry parameterization. And this, you can think of it, this is a geometry module. It will receive some control point displacement, and then its output is the new surface geometry coordinates. In this case, you can think of it's the surface mesh. So we receive some control point displacement, do some computation to actually change the surface mesh geometry. Again, because it's the baseline design, we will not change. We're going to use the baseline surface mesh. And then we go to the 4th module. You can think of this as the mesh module. The mesh module basically receive the new surface mesh, and then to deform the volume mesh. As I mentioned, we only generate the mesh once. We will never regenerate the mesh because that will be slow. So that's why we deform the mesh. We will have a new surface mesh, we deform the volume mesh, and give it to the flow solver for the CFD. The CFD will receive a new mesh with a new design surface geometry and do some computation to compute the number 6 data, state variables, and the objective function. Okay, so this number 5 module has 2 outputs. And then the adjoint solver will receive the flow variables and compute the derivatives. Then we give the objective function values and the derivative of the objective function back to the optimizers to do some and use some algorithms to update the design variables. We essentially update the location of the control point to change the surface geometry, and then generate a new mesh or deform a new mesh, give it to the flow solver, adjoint solver, repeat this loop until the optimization converges. That's the overall the process. But in the next few slides, I'm going to talk about some details of each components. Any questions so far? Very good. All right, let's go to the next slides, which is the pre-processing module. And as I mentioned, it's the module number 1. And the goal is to generate mesh and free-form deformation control points. And the mesh needs to be in the OpenFOAM formats. And the possible tools are you can use broad mesh, snappy hassle mesh. These are the utility from OpenFOAM. If you are familiar with OpenFOAM, you probably used this utility before. And also, we can use this software called PyHip. This is specially designed for generating airfoil and wing mesh. You can generate very high quality mesh, structural mesh, and PyHip only generates structural meshes. And then, also, of course, you can use commercial software such as iSim and PointWise. So for the FFD points, it needs to be in a Plot 3D formats, and you can use some Python script we provide, such as GenFFD. We're going to explain what is this file, what's in this file later. And also you can use commercial software, but you need to convert it in a Plot 3D format. After pre-processing is done, we go to the optimizers. The goal is to receive some function values and the derivative values in updated design variables. And we are going to use the PyOptSparse, this software, to set out the optimization province. Again, by the way, all the components in this MACH-Aero framework is open source. And PyOptSparse essentially will help you to set up design variables, objective and constraint functions, and optimizers. And PyOptSparse actually supports quite a few optimizers, but in the DAFoam tutorials, we only provide some settings for these three optimizers: SNOpt, SCR-SQP, and IPOpt. SNOpt is commercial software, so you have to buy the license, but SCR-SQP and IPOpt, they are open source software. Okay, here is basically an example of how does, if you are not very familiar with what is the gradient-based optimization, is that in this type of algorithm, you will start with a baseline design. If you think of this as the plot contour of your design space, you will start with a baseline designs, you will compute the gradients, it will then you will find the most promising direction in the design space, for example, these directions, and take a step in these directions to improve the design and repeat this process for multiple iterations. Eventually, you will be able to find the minimum point. Okay, that's how a gradient-based optimization algorithm work. All right, so after the optimizer module, we have this geometry module, and as I mentioned, its goal is to receive the updated design variable to actually change the design surface geometry or surface mesh. So we use the PyGL module to do that through a so-called free-form deformation approach, FFD approach. I think this is a very important step. By the way, the reason I want to mention all these modules is because in the DAFoam run script, we need to provide the parameters and setup for all these modules. So I think that's very necessary to explain what's the input and output of all of these modules and how do they work. So this PyGL use the FFD approach. These red points are the FFD control points. So as I mentioned, you need to generate these points in the pre-processing step. Okay, so once you can imagine that once you generate this FFD points and then you put your design surface geometry, in this case, this aircraft, and into this FFD points, and this FFD point will somehow snap to all these surface geometries. Then after that, once you move this, for example, control points up, and then the surface geometry of this aircraft will change. That's the way we change the surface geometry. We do not directly change the surface mesh. Instead, we change the control points. There are two main reasons to do that. First is because if you change the control point, the deformation and change of the surface geometry will be very smooth. And the second reason is that we can reduce the number of points we can control. We need to control, right? So you don't want to control all the surface mesh points. There are so many, and you will create a lot of discontinuity. So that's the reason we want to use this FFD approach. Now, once we get a new surface mesh, as I mentioned, that we are going to deform the mesh. That's what we do in this mesh module, and receive the design surface mesh, which is the update one, to update the volume mesh. Here is an example. We use the IDWAP, this module, and it actually implements an inverse distance weighting method to deform the mesh in a very smooth way. And it works for both structured and non-structured meshes, and also works for 2D and 3D cases. Although here I only show you a 2D case with structured mesh. You can see that if you move this control point down, it was here. If you move it down, that the surface geometry, which is your design surface, will change. And the surface mesh, of course, will also change. Then at the same time, we also deform the volume mesh. Otherwise, we will get negative volume mesh, negative volume. That's not good for CFD. So this mesh deformation is very smooth. All right, so next module is the flow simulations. The goal is to receive the new mesh and run flow simulations, compute objective function, Also, sometimes we also need to compute constraint functions, as well as the state variables such as velocity and pressure. And we use the OpenFOAM to run simulations. As I mentioned, we never run the OpenFOAM's binary solvers. Instead, we compile all these OpenFOAM solver into C++ libraries and call them from Python. The main reason to do that is that we want to get rid of all the file IO operations. If you run OpenFOAM before, you know that OpenFOAM, how it works is that you will read some informations from file and run some simulations, output some files to the disk, and then read some file in. This process is slow and it's not very convenient. If you want to do optimization, we want everything happens in the memory. And it's very easy to transfer data between the components. That's why we want to compile everything into libraries and call them from Python. All right. Okay. The last module is the Agile solver. Okay, so that's essentially DAFoam. You will receive the flow variables and compute the total derivatives of all the objective functions with respect to all the design variables. DAFoam implements efficient derivative computation method using the so-called Jacobian-free Agile method. And the derivatives machine precision accuracy. This is a diagram that explains how does that work. Of course, today we don't have time to explain the details, but if you're interested, you can check the DAFoam paper. So I would like to emphasize that this machine precision accurate Agile was just recently implemented. All right, so that was the two very brief introduction to the DAFoam and to the MACH-Aero Framework. Now we have some hands-on examples.
Sorry, Ping, may I just ask a question?
Please go ahead.
Yes, on the previous slide where you mentioned, so it receives the state variables and compute the total derivatives of the objective functions with respect to all designed variables. Does it also calculate the constraints with the derivatives of the constraints with respect to the design variables?
That's a good question. Yes. So I should have said that objective function and constraint depends on. So let me give you a specific example. For example, if you are running an airfoil aerodynamic shell optimizations, you might set up two functions, the drag and lift. Then when you run DAFoam, it will compute the total derivatives of drag with respect to all the design variables, as well as lift with respect to all the design variables. And in design optimization, you are going to use the drag as the objective function. You are going to use the lift as the constraint, which means, yes, they will definitely will compute the total derivatives of all the functions, including objective and constraint function with respect to all the design variables.
Okay, understand. And in the case of geometric constraints, it's just greater or equal. There are no derivatives in that case.
That's also a very good question. Let me go back to this slide that explains. Okay, so let's look at this diagram. And we were talking about module 6, right? So it will compute the derivatives of objective and constraint functions. Okay, and another constraint is computed by module 3. So if you have geometry constraints, for example, if you have a volume constraint, then this type of constraint will be computed by PyGL, which is the module number 3. If you look at the output of this module, it will output update the surface geometry as well as some geometry constraints and the derivatives. For example, when you run this, when you receive a new FFT control points and then do some computation, the one of the outputs is the update surface mesh. The other output is for example, if you set out a volume constraint, this module will output the volume of your wing as well, whereas the total derivatives of your volume with respect to all the design variables. This is automatically done by PyGL. You don't actually need to manually set out anything. As long as you say, okay, I set out a volume constraints, then this module will automatically compute everything for you, including the value and the derivatives.
Okay, understand. Thank you very much for your answers.
Hi, I would also like to ask a question.
Sure, please.
In the next slide.
This one?
The slide of adjoint.
Okay, so I can go to that one, this one.
Yeah, this one. Here we can see like in the 8th number box, partial R by partial X. Now here, the partial R means the residuals, the change in residuals. Residuals are basically generated by the flow equations. So as we say that we solve the flow equations once in case of adjoint. So when we change the design variables, would partial R remain like would partial R will be computed without this without solving the flow? Like how we are going to compute partial R by partial X without solving the flow each time we change the delta X like design variable?
All right, so I guess your question is that do we need to recompute the flow? No, we do not. So let's take this partial R, partial X as an example. So when we compute this, there are two ways to compute. In this diagram, we are using the so-called automatic differentiation to compare it. It needs a lot of explanation. Let's assume that we want to use the finite difference method to compute partial R, partial X, right? So let's then assume that our X is just one control point. We only have one design variable, okay? Then what we do is that we first solve the flow, converge your steady state CFD, then we have a converged residual. Okay, they should be very close to 0. Then what we do is that we perturb this X. For example, X, the initial coordinates displacement is just 0. Then you converge the CFD, you get very close to 0 residuals. All the residuals are 0. Then what we do is that we perturb this X by 0.01 meters, for example, and then we don't resolve the CFD. Instead, we just call the function to recompute the residuals. Okay. So, which means that our state variables, all the flow variables, velocity and pressures, they will be the same. They are the converged flow field. But you change the geometry. For example, you change the control point displacement, your surface geometry, an entire mesh will change, right? So when you perturb the FFD points, we are going to update the surface geometry, surface mesh. We're going to also update the volume match coordinates. So your geometry changes. Then when you recompute the residuals, don't solve the flow, do not resolve the flow. Instead, just compute the residuals. Your residual will be off, will no longer be 0. Then we take the difference between the R perturbed minus R original divided by delta X. You can compute the partial R, partial X. You don't need to resolve the flow. Does that answer your question?
No, I don't get this point that as I said earlier that residuals are like being generated by solving the flow. So if you're not solving the flow, then how we are finding the change in residual?
Right. So actually, if you are familiar with the implementation of CFD, in the CFD, what we do is that we usually have, for example, steady state CFD. We have, say, I run a CFD. I need 1,000 iterations, right? So actually, in each iterations, you are trying to use some methods. For example, you are using some linear equation solvers to converge the residual to 0, which means that you do need to compute the residuals, converge the residual to 0, and go to the next step. So in this process, you are computing the residuals. So we have already identified some functions to compute the residuals, and instead of resolving the flow. So if you look at the computer in fluids paper, we have an example of a specific example of what are the functions we use to compute the residuals for open flow. And during the flow simulations, we are trying to solve this residual equation for multiple times.
All right. Thank you so much.
Great. Thanks for the question. Any more questions for this framework? All right. If not, I guess we can move on to the next section, which we will have some hands-on examples. I like the discussion we have. So let's make this workshop more interactive. Now, so we go to the topic 3, which is the airfoil aerodynamic optimizations. In this section, we have quite a few topics: how to use the Docker image, how to run operation, how to visualize the result, how to read the log file. I think this is very important because Sometimes your case is not running very well. How do you identify which part is not working? And the details of configuration files and how to change them. Okay, how to use DAFoam Docker image. So in the email I sent out earlier, and I assume that hopefully you have managed to install this Docker, this software. And because we're going to use that to run cases, you don't have to compile everything. And this is the most straightforward way to run DAFoam. Of course, you can, if you have already compiled everything from scratch on a computer, you can use that. But let's assume that you have not. Most of you probably have not done that. But today we can use this so-called Docker image. First, please follow this link to install Docker. And I'm going to copy this link. Okay, so I'm going to actually it's here. And let me know if you cannot see my screen. I'm now looking at the DAFoam documentation website. And if you go to the download image, there are some instructions on how do you install. If you are using Ubuntu, follow this instruction. You are using Mac OS, follow this instruction. If you are using Windows 10, follow this instruction. If your Windows 10 version is home, then there are some actual steps you need to do. So let's assume that you have already done that. Now, after done, verify the installation by running this command. If you are running Mac or a Windows system, you have to open this Docker app. So I now open this Docker app and going to let's do some interactive stuff. Move this window here and can you see my terminal? Let me know if you cannot see my terminal. I'm showing two things. One is the PDF, the other is the terminal. So once you install, you can run this command. Let me clean this first. Docker version. You should be able to see some output here. Otherwise, your Docker installation probably is not right. Then right after that, and you can download the Docker image. I suggest everyone should, and you can open a terminal if you are using Mac OS or Linux. If you are using Windows 10, open the so-called prompt command window. And of course, before that, open the Docker app. So, and after that, you can just run this command. You should be able to, download that, or I already download it. So that's why when I hit enter, it says, oh, it's already up to date. Maybe downloading this images is about 1 GB, so it may take you 2 to 5 minutes, depending on your internet speed. But a few other, while you are downloading, I want to show you a few other commands that are very useful. For example, Docker images. Before that, let me Docker image. So this will show all the images you have already done. Let me maximize this window. So it will show all the images you have already downloaded. I download 2 images, version 2.25 and 2.13. So, and the size and this kind of stuff. And another very useful command is this command, Docker ps-a. So this will show all the running containers you have. I have nothing, so that's why I see no outputs. That's basically the 2 main commands you want to check. Now, then you can also download the workshop material from this address. Let me copy this and paste it here. Let me start a new, So all the materials are from here. And if you can click the link, you can click this code, download zip. And I already downloaded to my desktop, but you can download to your home directories. Inside this workshop folder, you can see here slides. This is the slide I'm presenting right now. And also there are some examples. We're going to run those examples actually now. So once you download this, I guess, we can move on to the next step. Oops. So this one. So then the next thing you need to do is that you need to use this cd command. Again, we assume you are familiar with command line. Cd is a command to go to a directory. You go to the directories of this workshop you just download. So for me, I'm going to claim this. I already entered directories is called actual node. I'm gonna this. You can see this is the zip file I just download. I'm going to go to this workshop main. Okay, so ls. I can see some 2021 summer, and go to 2021 summer, and go to examples, and go to this one, and go to incompressible. Actually, you can see I have a converge case, but I will assume that this is my first time running this, and go to incompressible. And if you type ls, and you should be able to see that these files, make sure you are in the correct directory before you run this command. In Windows, this ls command is dir. For the Linux and Mac, this command is ls. Okay, so after that, you can run this command. I'm going to copy this and use in Mac. That's why I copy this command lines. If you run this, if you hit enter, you should be able to see something like this. After you run this command, you will be in a so-called Docker container. And here is the command you should see, the output you should see. Of course, if you use Windows, open the prop command terminals and run this command. Anybody has any issues running this command to go into the container? Okay. If not, I will assume that you are already in the Docker container and I'm going to move on. But before that, let me explain. Probably you are still downloading the image. So a few things I want to mention. What does this about command do is that it will start a so-called container. You can think of container as a virtual machine. You are running another system on your computer. This system will be Ubuntu system. Then you are going to run DAFoam on that system. So the next thing this command will do is you will mount or link your computer's current directories, which is this case directories, to the containers, this mounted directory, such that they can see the same thing. They can exchange data. After that, you will log into the container, and as the DAFoam user, the username is DAFoam user. This is the machine name, is a bunch of random numbers, and you are in the mount directory. If you're in the mount directory, if you type ls, you will see the same thing, but now you are no longer on your local computer. You are in a container which runs an Ubuntu system. Okay. Of course, you set some other relevant environmental variables. A few notes: treat this container as disposable. Run one job, open one container, run one job. Once it's done, exit. And do not store any information. And also, this DAFoam user has sudo permission. Its password is this. Okay. Now let's run case and how to run the optimization. So the way we run this is we go to this directory. This is a summary of this case. It's a Naga double 12 case. Very coarse mesh. We have 20 FFT points. I'm going to show you how to visualize this point, but the objective function is CD, and constraints CL, and velocity is 10 meters per second, very, very low speed, and Reynolds number is relatively low. And we have the SA model. And the constraints, we have some other constraints. We're going to explain the details later. But let's just make sure that everybody managed to run the case. Okay. So as I mentioned, once you're in the container, you should see something like this. And I see something like this. And then you can run the command ls. So now, remember, you are already in a container. It doesn't matter you are using Windows or it doesn't matter you are using Mac. The command will be all the same. You should be able to see this. Make sure you see this, which means that you are in a correct directory. Then what's next? What's next is that you are going to run this command. There are two steps to run a case for all the tutorials. They are the same. The first step is do pre-processing. If you remember the diagram, the pre-processing is that you just run the script to generate the mesh. I'm going to copy this script and run it. So you can see that it may take a couple of seconds to generate the mesh. You should be able to see the mesh generation done. Okay. Right after that, you copy this command and run it. So when I hit enter, so I should be able to see a bunch of outputs. You can see that, well, once you run this command, what will happen is that optimization will run, and you will print all the log file to the screen and also save it to this file, logopt.txt. This is through this command. So in addition, the optimizer will write a separate log file to the disk. This for the IP optimizer we use is this log file is called opt IP-opt. Later on, you will see that you need to monitor both of the two files for the progress of this optimization. But if you just look at this and the solve CI is done, and then we are running some coloring solvers, I will let it running, okay? So this case actually took about 10 minutes on my computer. It converged in 17 steps. So while you are waiting, so you can let this window run and don't kill it yet. So I'm going to open a separate terminal, okay? So I'm going to show you a separate terminal here. And so you can go to the same directories. Let me clear workshop. You can always go to the examples, MACH-Aero. So this is the directory we just in. So you can see that while the optimization is running, it generates some extra files compared with the original case. And then we are going to explain what are these actual files, what do they mean? And also we're going to explain how do you read outputs. So if you ls, I think we will soon to see a second file. Okay, so this is so you see, before it was 0.0001, this is the baseline design flow, so flow results. 0.02, we are at a second iteration. All right. Actually, in this workshop, I am going to pretend I already ran this case before, but if you want, you can keep your job running. And because we are not going to wait for 10 minutes to, to visualize, to check the results, I'm going to just show you how to visualize the result. So for now, I'm going to kill this job. Okay, to kill this job, you just press Control-C. And you, if you cannot, you press this command, Control \. Let me see which one. Click this command, Control \, or press Control-C multiple times. Now this job is killed. Now you can see that I'm still in the container. I want to exit it. So I click exit. I go back to my, I managed to go back to my local computer. So if you want this, let this job running is fine. So again, I'm going to pretend I already run this and I'm going to visualize it. How do we do that? We use ParaView. Right, so we use ParaView, this software I'm going to show you. And again, I'm going to assume that you already download ParaViews from this address. If you go to here, if you go to this address, so they have a download sections. You can select which version. I use 5.8. They have different version, Mac, Linux, and Windows. Very straightforward to use. Okay. So once you download this, again, I'm going to assume that you already download this. And how to use that. So first, you need to open it. So I open it, and you click this open a case. Which case I want to open is the case we just ran. But I already ran this case, and I don't want to run it again because of the time being. That's why I want to directly load it from my local disk. So the way you load it is click this open file and then select the form paraview.form, this file. Okay. Once you select this file, you hit apply. Okay, you hit apply, you should see this. So I have quite a few things in these slides. I'm not going to read these slides because I'm going to show you directly how do you do that in ParaView. So we are going to show you a few things. First, once you are in here, you can see that this is an airfoil, although it looks like circle, but the airfoil is in the middle. On the left panel, you have some case you are running and the mesh you are selecting, some variables. And the first thing I do is I will switch on this advanced properties. By default, it's off. I need to click on, and I'm going to scroll down to the very bottom and check this camera parallel projection. This will allow you to view the case better. So I usually check that. After that, I will use my mouse wheel to zoom in. If you scroll it, you should be able to zoom in this. All right, zoom in, and then if you click the right click your mouse and hold it. Oh, sorry. Actually click your mouse wheel and hold it. You can pan this. You can drag this, airfoil around. You can zoom in, choose a very nice angle. Another thing you want to do is that you can scroll up. Okay, so you can view different variables. Right now, it was showing you P is the pressure, U is the velocity, and you can view other variables very easily. And also you can choose different surface representation. You can choose surface with edge. We'll show you the mesh. And sometimes you want to switch off the variables, just show solid colors. That's the mesh. That's the way you visualize the mesh. But for now, I want to visualize the pressure. I'm going to use surface. Okay. Then another thing you may want to do is to adjust the range of this pressure variables. Right now, by default, you give you this range is automatically determined. But if you want to change it manually, of course, you can say I want some round down number. So minus 85 to 50, you can get this very easily. So one more thing I want to check is after that is done, you can press this play button. So I assume that you already run this simulation optimization. Once you hit the run button, you can see that you can play a movie that this case ran for 70 steps. And if you want to go back to the first frame, so you can hit the play. You can play again. Sometimes if you want to loop this, you can keep playing and let it loop. So you essentially plot the evolution of your optimization history. The step size is showing here. Okay, these are very basic usage of Paraview. Of course, you can check online some more advanced usage. But that today I do want to show you something, and that is also very basic, is how do you plot the pressure profile? Now we can see a lot of contours. How do you plot the profile? The way you plot it is that to plot a profile, we probably need to cut a slice. So to do that before, we need to uncheck the internal mesh. This is the volume mesh you are seeing. So we want to check only the wing mesh. Well, I should have called it airfoil instead, but let's say just a wing. Hit apply, so it's gone. But you can use your left mouse and drag it to rotate a little bit. You should be able to see this airfoil here. And then the next step is click here, this one, slice on top. Okay, so if you click a slice, by default, you cut a slice in the X direction, but we don't want to do that. We want to cut a slice in the Z direction, which is the span wise. So you can see that cut a slice in the middle of this airfoil, and then I will hit apply. Okay. Once you hit apply, you should be able to see some airfoil profile that is cut in the middle span of this airfoil mesh, and it has some color in it. That's pressure. How do you plot it? Well, you can right click this slice one. You just cut, set, then go to the add filter, select data analysis, and then select this, plot on sorted lines. This is very important because you want to sort the lines. Okay, so especially for unstructured mesh. So you want to plot on sorted line, you hit apply, and then you can see some plot showing up and right. Okay, but it's the plot is not looking very good because you need to go back to here to your left panel, scroll down. Okay, the X array is the X-axis. We want to select the X coordinate is point X, because the X here is the clockwise direction. We want to select this. Okay, now it's looking much better, but still you are plotting a lot of variables. We don't want to plot all of them. We only want to plot the pressure. So uncheck everything except for the pressure. Now you see that, well, on the right panel, you see the pressure distribution. So if you're not very happy with Paraview's plotting, you can also output the data. If you select file, save data, okay, then it will be in a CSV file, and you should be able to plot them using some other software such as Python. Okay. So, all right, this is the Paraview. I guess I cover everything here. So in the next section, we're going to learn how to read optimization log file. And then the first section is over. Let's take about 10 minutes breaks. Let's, by the way, so far, any questions? Okay, if not, I suggest we take a 10 minutes breaks. Let's come back in 10 minutes. Okay. Thank you very much. I'm going to pause the recording and I will restart in 10 minutes. Okay, welcome back. This is the second section of the workshop. In the last section, we managed to, hopefully we managed to run some the Airfoil aerodynamic share optimization using Docker image. Now let's look at how do we read the optimization log files. Okay. Well, so the very first file we need to check is this file, obd_ipop.txt. If you use the different optimizer, the ipop can be replaced to another name, for example, SNOpt. This is the file that is directly output by the optimizer instead of our DAFoam framework. So if you look at this, we want to check basically three main things. First is the objective. The second is the so-called feasibility. It's the violation of your constraints. And the third one is optimality. You can think of this as a quantity that measures the gradients. If it's very close to zero, then you are probably very close to a local minimum point. So a successful optimization should reduce the objective function. You should see that objective function is reducing. Otherwise, something is very, very wrong. And the feasibility optimality should drop below the prescribed tolerance. In this case, we set it to 1e-6. In the wrong script of pi, we are going to talk about that later. Okay. If you look at the output, if you open this file, let me do a little bit interactive. I'm going to go back to here. Let me see what I have. I'm going to clean out the results. I'm going to go to this converge case. For you, you don't have this. So you don't have this because I already ran, as I mentioned, I already ran this case. So that's why I go to converge. For you is probably just incompressible. So in this, folder, you can see many files. I'm going to explain what are they later, but you want to check this file first, obd, this file. So let me open this file. Okay, obd ipop. Okay, now what I want to do is that switch on the what mesh number, no wrap. So if you open this file, you can see a bunch of outputs, but the actual very useful things start from line 25. So iterations and objectives. This column shows you the evolution of your objective function. Initial objective function at iteration 0 is this value. And if you go down here, the optimized objective function obviously is less than this. And then the objective function is reducing, that's good news. The second thing you want to look at is this parameters, is the feasibility. Of course, different optimizer may call them differently, but this is the feasibility. And at converge, in the beginning is 1e-7, very good. At converge, 2.5 e-9. It's well converged. Very similarly, you want to look at optimality. In the very beginning, it's only 1e-2. It's not very good, but after it converges, it drops to 5.6 e-7. So this case is well converged. So we can consider that's a successful case. But in practical, when you run large scale optimization cases, especially if you have hundreds of design variables, sometimes, well, the optimality probably will not drop to 1e-7, but as long as it has a several magnitude of drop, that should be okay. Okay, that's the very first thing you should look at after the optimization is done. Now, next, I'm going to talk about more details about the log files. But before that, I want to very briefly mention what equations we are solving. For this case, we are using the so-called simple form, which is an incompressible flow solver that solves the obviously incompressible version of NS equation. It's a steady state simulations. There's the governing equations. In the adjoint solution, we are actually solving these two sets of equations. The first one, we call it an adjoint equation. It's a linear equation. So we can compute the left-hand side matrix, right-hand side vector. We solve the linear equation, we get an adjoint vector psi. And then we plug in the psi to compute the total derivatives. Very, very straightforward. The second step is usually easier than the first step because the adjoint equation is usually very large and you need to have a very good preconditional to solve it. But this is automatically handled in DAFoam. All right. Now, so we have know this. It looks like from this file, this case is running well. What's next? Well, this file log opd.t. Please go ahead.
Ping, may I interrupt you to ask a question about the first log file that you've shown? So I've run DAFoam a few times, but I've never seen this particular file. I guess it's because it's the different optimizer that I've been using, probably the SNOpt instead of the IPOPT. I would like to know in terms of results, which is really the best for the optimizer?
Yeah, okay, so that you're right. So because I guess by default, for the older tutorials I post online, they use SLSQP as the default optimizer. That's probably why you don't see this file. This IPOpt is also an open source optimizer. We set it in this tutorial is mainly because it has more information. Obviously, they all use very different, not very different. They use different algorithms to do optimization. For the SLSQP, the output for this file is very, very simple. It just print out the objective function map. It does not have the feasibility. It does not have the optimality. So SLSQP is kind of very old optimizer. And we set it as a default is because it's open source, very straightforward to very little information. It's very easy. That's very first. But this IPOpt is always more advanced. And I don't think people are still maintaining SLSQP, but people are still maintaining, updating this IPOpt very frequently. So you can see a lot of information you can see, especially this feasibility and optimality. We really want to look at it because why? If you see our objective functions dropping like this, and then it's kind of plateaued, become flat, but it doesn't mean that your optimization has, you cannot say for sure that if you see that objective function is no longer changing, but is this case actually really converging? The second thing you want to look is the optimality. If at a point the gradient is almost zero, you can say that, okay, this is a local minimum point. Why? Is because that for a lot of cases, for example, if your gradient is not accurate, then your objective function cannot further decrease. That's possible because the gradient is not accurate. The optimizer cannot find a new design that is better than the previous design, not because you're at a local minimum point, but because your gradient is not accurate. Then it will struggle. You can still see the objective function become flat, but that doesn't mean that the case is converging well. In terms of the optimizer, well, we use SNOpt for all of our publications. This is because we think that's a more advanced optimizer. We know more about it, and we are more familiar with them. We have some special good configuration we think we have been using for many years. That's why we use SNOpt. And also SNOpt have some good features such as the fail flag, this kind of feature that IPOpt does not have. That can very efficiently handle bad mesh quality. But this is a commercial software. I can't just distribute it. So that's why I use IPOpt in this tutorial.
Okay, understand. Just a quick question on the other columns, the LG, Mu, and the D, and these other four columns. What do those represent?
Well, they probably, I'm not very familiar with it, but they probably means the penalty function and penalty parameter, because IPOpt use an interior point method to do optimizations. They set out penalty functions that I think these are the parameters for that function.
Okay, understand.
Yeah.
Okay, thank you very much.
Yeah, okay. Thank you for the question. Very good.
Sure.
Very good. All right, so now let's look at the second file. Once you confirm, as I mentioned, once you confirm, okay, the case is running and the optimality, feasibility, they both drop to below your prescribed tolerance. The second file you want to look at is logopt.txt. So let's just open this file. So it should be in your optimization folder, and then I'm going to set no wrap and then set out the line number. Okay, so there are a lot of outputs. Actually, if I go to the bottom, you have 7,000 lines in this file. It's a lot, but we want to look at just a few things. For example, I'm going to now put these slides on the left and the log file on the right. The very first thing you can look at is the mesh counts. So say, for example, after the optimization is done, you want to check what's your mesh, you can check line 52, global cells. This case has 4,000 cells, very coarse. And the second thing you can look at, and if you scroll down, and actually I'm going to scroll down by page, so it will print all the DAFoN options. And after the case is run, sometimes you still want to check, okay, did I set this parameter right? You can always look back in the log file because it will print out all the DAFoN options you set for this run. So there's a lot of options. And right after that, you can see this all IDOP options. IDOP, if you remember, that's the mesh module we use to form the mesh. You will also print all the options. Right after that, you get the surface. This is a so-called symmetry plane informations. You have two symmetry planes. Actually, it's here. So because it's an airfoil case, we have two symmetry planes. We I want to highlight that DAFoam does not support pure 2D case. So we set up actually 3D case to mimic the 2D airfoil flow simulation optimization by setting two symmetry planes. Okay, then you need to set a symmetry planes. I will explain the details later. But right after that, what's that? Well, I'm going to go to the next page. Right after that, we go into a mode called solve CL. What does this do? But if you are familiar with the airfoil aerodynamic share optimization, and what we do is that we set out the control point as the design variable. We also use the angle of attack as the design variables. But we have a lift constraint, which means that your initial angle of attack should give you the prescribed or target lift coefficient. In this case, we want the lift coefficient to be 0.5. Which angle of attack will give you lift of 0.5? You don't know before you run optimization. That's why before you run optimization, this will be automatically run. So it will use the so-called solve CL mode to find the angle of attack that gives you CL 0.5. This is done by doing some finite difference search. It's very, very straightforward. But before that, we want to read it. Like we give a tolerance this, max iteration, and it will start solving the flow.
Sorry to interrupt. I would like to ask you a question that can we apply the inequality constraint over CL?
Quality constraint. Can you be more specific?
Inequality constraint.
Yes, yeah. We can give inequality constraint. In this case, we get equality constraint. Yes, we can give inequality constraint. This will be set up in the run script of pi. We were going to talk about that later.
All right.
So by the way, yeah, talking about this, yes, the way we set up CL constraint is that we give a lower bound and upper bound. So we just say lower bound is 0.5, upper bound is 0.5. This becomes an equality constraint. But if you set lower bound is some value, upper bound is some other value, give a range, yeah, this becomes an inequality constraint. All right.
May I ask another question, please?
Sure. All right.
Yes. So it's regarding the angle of attack, and so there you have the constraint lift. Let's say, for example, as you have it here on the slide of 0.5. But let's say you already have, and you already know what the angle of attack will be, so you don't need the DAFoam to really calculate that, because let's say you are running a simulation from a baseline design that you already know. So for example, the existing NACA 0012, which the data already exists at what particular lift gives you a particular angle of attack and so forth. So essentially my question is, if you decide to fix this lift, this angle of attack within the run script document or within the run script, can you do that, or do you really have to allow DAFoam to run to do the calculation of your alpha, your angle of attack?
Okay, yes. Well, there is a line that you can comment out that you don't have to run this mode if you are pretty sure that, I will talk about that, this is in the run script. You can comment out 2 lines, then you don't have to run this solve here. We assume that you don't know the angle of attack now, because you might change something. As long as you change anything, then this angle of attack will change. So you don't have to manually run it every time. But of course, if you already know the angle of attack, yeah, you don't have to run it. But if you know that, you still can run it. It will run one flow simulation. It will return, okay, your angle of attack is already correct value. It will not harm anything. So you can still run it, no problem.
Okay, so if I understand correctly, I can actually input the angle of attack that I would like it to consider.
I say again, can you say your question again?
Sure. If I understand correctly, I can actually input the angle of attack that I would like it to consider without it doing the calculation. So let's say at the target lift of 0.5, let's say I would like it to consider at an angle of attack of, I don't know, 0.35. Can I input that in the preliminary, in the input values without it having to do the calculation on? If it does the calculation, what will it give back as a result? That there is a contradiction between what it calculated and what I inputted, or what?
So even these solves here, we still need to give initial angle of attack. So, and let me go back to just make sure that let's forget about this. Let's go to the run script. So I'm in the run script now. I'm going to go back to this line, well, this line 37. You still need to give an angle of attack. I can give any value because I know that solves here will return the correct value for me. But of course, if you already know this value, just set this value to whatever, maybe 3.5, or you know the exact value, just set it here. And the solve here will just run once, and you will figure out, okay, that's the correct angle of attack. Then you will not run. Well, you will run once.
Okay. Okay.
Does that make sense?
Yes, it does. Thank you.
Okay, that's very good. Yes, the bottom line is that you still need to prescribe the initial angle of attack, even though it does not match the CL. It doesn't matter. If it match, that's great. Oh, by the way, I'm going to go to the line that around this. So if you look at task optimization in line 227, these two lines are running the source here. But if you don't want to run it, just you can comment this out, and you are pretty sure your alpha 0 is correct. But let's assume that our alpha 0 is not correct. I will just give it some random number, and then you can just automatically get the correct angle of attack.
Okay, understand. Okay, thanks.
Sorry, I had this, like the same concern as the person before me. So you said if you know already the angle of attack, you can put it and the optimization won't change it. But what does it mean if you already know that it will match the lift? Like, can you just set like a constraint on the lift, any constraint on the angle of attack, just wanted it not to change and have the best shape for that?
Okay. That's, I guess I was not very clear about this. When I say for example, you know, alpha 0 3.5 will give you CL 0.5. This is our target lift. Then you set it here. And the solve CL will not change the number for the first flow simulation. But later on, optimizer has the complete freedom to change its alpha. Alpha 0 means the initial angle of attack for the 0 iteration, basically the baseline design. You know that alpha 3.5 will give you CL 0.5 for your baseline design, but you don't know what's alpha will give you the correct lift for the optimized design or the second iteration, third iterations. This is up to the optimizer to decide.
Okay, so we have to make sure if we want to set the angle of attack as a fixed parameter, that for the first iteration, the alpha is matching the CL.
That's right. That's right.
Okay.
That's actually very important because you don't want to start with a design that has CL is 0.5, which means you start with a design that's not feasible. That's not good. We usually want to make sure your baseline design is feasible. All the constraints should be satisfied.
Okay, so, okay. Thank you.
All right, very good. Thank you. Okay, so now where were we? Okay, so we were talking about this one, right? So let me set up the correct set number. We were talking about solve CL. Let's go back to the place where solve CL starts. Okay, this is a solve CL. Okay, so it will essentially run some flow simulation to figure out which alpha match your target lift for the baseline design. So I'm going to fast forward, go back to the next flow. It will solve a couple of flow simulations. You don't have to touch it. Well, actually solve quite a few. After that, the output is that say completed. Okay, so it says this alpha 5.139185 will give you CL 0.5. Okay, then that's it. it will use this alpha as the initial design variables. If you look at the summary of this optimization, I'm going to go to the next slide. Okay, right after soft here, we will, the pile sparse will print out the optimization configurations. That includes, what are your objective function? In this case, objectives is CD, is a drag, and design variables has alpha and shape. You can see that at alpha lower bound 0 and alpha upper bound is 10. And the value is the value we just got, 5.13. For the shape variables, the lower bound is -10, or -1, upper bound is -1, as the initial values are all zeros because there's no displacement. Okay. Of course, in addition to the design variables, we also print out the constraints, and you have the type of constraint, volume constraint, thickness constraints, a lot of other constraints, and the values in the upper lower bounds. Okay, let me go back to here. Let's go to the, oops. Okay, so in addition to the thickness constraint, we have a CL constraint. You can see that CL constraints here, and our lower bound is 0.5, upper bound is 0.5. Okay. Okay, I'm going to go back to here. Oops. Okay, right after this, we are going to go to the next page. Okay, this one. After that, we are going to run the so-called coloring solver. This is some coloring information we are going to need to use to compute our preconditional. So this is fully automatic. There's nothing probably you need to look at here. After this, by the way, this coloring solver needs to be run only once. Okay. Once this coloring solver is done, we get a sufficient information, then we can start the first flow simulations. The number looks strange. You should have said 0.000, but the reason it says 0.005 or 0.05 is because we already ran some flow simulation for salts here. So, but remember, this is your first flow simulations. Then you can see that, well, when you run the first flow simulation, you say evaluating objective function 0.05. It will first print out your design variable values. In this case, our alpha is already 5.13, and the shape variable are all zeros. So you can correspond to this log to the some columns here. And then it will define the mesh because we have, you can see that it's defining the mesh, changing the volume mesh, but because we have all zero design variables, the mesh will essentially will not change. Then you will say that, oh, we are using IP ops. Then right after that, we are going to check the mesh quality. For each flow simulation, we are going to check the mesh quality using the OpenFOAM's check mesh libraries. So we return the maximal orthogonality and the skewness. Before that, you can see some other calls here that we are setting out some boundary conditions for at the far field. We set out the velocity components based on the angle of attack. You only prescribe, if you look at, I'm going to talk about that later, in the run script, you prescribe the magnitude of the velocity, but obviously velocity is a vector that depending on your angle of attack, the component will be very different. This is fully automatically done by DAFoam, that it will, based on the velocity magnitude and angle of attack, to prescribe the velocity components for velocity, for pressure, for the turbulence variables, and it will prescribe the boundary condition. It will override whatever boundary condition that is provided in the OpenFOAM 0 folder. So keep that in mind. Now, what's next is that we'll start some flow simulations, time equals 1.
May I interrupt, because I have a question?
Please go ahead.
Regarding the mesh quality, is it basically for information purposes, or does DAFoam react on mesh qualities? Like,
yes,
if it's not sufficient, will it somehow stop also?
Yeah, that's a good question. Well, if you look at mesh okay, means the mesh quality check passed. If it's not okay, for example, your skewness is greater than 4.0, you will say, okay, fail. What happened is that it will, first of all, there are two case scenarios. If your baseline designs mesh quality does not pass, it will not run the optimization at all. But another scenario is that, say, your first 5 iteration mesh quality has no problem, but at the 6th iteration, somehow your mesh quality is not good, skewness becomes 6.0. What will happen is that for this optimizer, it will not have the mechanism. It will consider, okay, this flow simulations will have the objective function with the same as before. But with the SNOP, this optimizer, it does has a mechanism to take care of this case. What will happen is that if you remember, when we do gradient-based operations, and we are going to compute the gradients and then compute the search directions, we are going to take a step size in the search directions. Let me explain this using this diagram. I think this plot is a good explanation. I showed it before here. Say, for example, your match quality is okay, but for some reason at this steps, it's already second step, your match quality is not okay. So you are supposed to find new points here, right? With the search direction and step side. But at this point, your match quality is not good. What SNOP will do is that we'll backtrack the step size, reduce to 1/10 of the initial step size. You will try to find a point here instead of here, because we know that the check match quality failed. Then you will reduce the step size, find a new point here, do the gradient search again. So this mechanism will handle this back match quality to some extent, but not completely. But it does has a mechanism to take care of this failed match quality.
Because I experienced with working with OpenFoam itself, not with DAFoam, that in some cases when the meshes really become complex, like not airfoils, but I don't know, like very weird internal flow channels or so, you might eventually want to accept some failed mesh checks because you cannot get rid of them, particularly not if you use snappy hex mesh. And in that case, DAFoam would not run. Like you have to have a good initial mesh.
That's right. So that's a very good case scenario. Actually, in this tutorial, if you look at 3D cases, so I can use my slides to show you that. Well, no, I probably don't have that. So DAFoam has the option to relax the track mesh threshold. Right now, the default value is, I think, is 70 degrees for the orthogonality and 4.0 for skewness. You can relax this. You can say, I can accept non-orthogonality being greater than 75. Then you can relax this. There is an option to relax that.
Okay, so it's operating with the same check mesh options that I have in general OpenFoam. That's
right. It's the same, but we can relax the tolerance. Say, for example, if skewness is 4.5, we can still return a mesh okay. So this can be set up in the run script.
Okay, good.
So actually, this will be used if you use snappy hassle mesh quite often. All right, very good questions. Thank you. Let's move on. We were talking about okay, the check mesh passed. Let's assume that this is a simple case, it passed, and it will run flow simulations. For this case, I think it ran for, well, very quick, like 200 steps, it converged and print out the residuals. For those, I assume that you are familiar with what is residual, but for those who are not very familiar, it's just essentially the you are solving a Gamma equations, the difference between the left hand side and right hand side. So if it's very small, which means that all the equations converge. And right after it converge, you want to look at a couple of things. First of all, if you look at this, and during the solution, you can see that the residual is printed. Okay, so we'll be already interested in the initial residual. And also what is printed to the screen is the Y+, which is very important because for this case, we use wall models, wall functions. That's why we have a Y+ about 60, mean Y+. But if you don't want to use wall function, then you need to reduce your Y+ to about maybe 1. Okay, so the CDCL is also printed to the screen. After it converges, actually it printed to the screen. And the value you want to look at is this value. Okay. So after this converged, the CDCL is printed to the screen right here. CD is this value, CL is this value, 0.5. So, okay, then you go to the next iterations. What will happen is we're going to solve the adjoint. So next iteration is adjoint, and the adjoint will basically compute the preconditional matrix, solve the adjoint equation. I'm not going to talk about details, but what you want to look at is the adjoint residual is reducing or not. So this is the, say, solving adjoint linear equations, the residual drops 8 orders of magnitude. That means that this case is running well, but for some reason that can happen that this adjoint is not convergent. very well, you need to change something. Okay. And because we have two objective functions CDCL, we need to solve the adjoint equation twice. Right after that, and it will compute the total derivatives, all the sensitivity will be printed to the screen here. It's a lot of information, but you probably don't need to look at those unless you are developing something. And this section of the sensitivity of all the objective function with respect to all the design variables, including the constraint function. Okay, right after the adjoint simulation is done, we get the efficient, we get enough information for the optimizer. We give this objective function value and the gradients to the optimizer. Optimizer will be able to design a new design variable. If you look at this, and this is the first, second iterations, and the flow simulation, of course, then he actually optimizer changed the angle of attack and the shape variables to this value. It was 0 in the first iteration. So then you will solve the flow again and prescribe the new boundary condition based on the new angle of attack, and then check the mesh quality again, solve the flow. I'm going to fast forward a little bit. Okay, so now if you look at a converged case, the CL is slightly lower than 0.5, but that's fine. So, but in the drag is reduced. Right after that, solve the adjoint, solve the flow, solve the adjoint until it converges. Okay, if you look at this log, basically saying the same thing. So I'm going to fast forward, go to the very end. Once this case converged, and the log file will print out some converged, the summary of the converged optimization, especially how many times, actually, how much time does this takes as 700 seconds, about 10 minutes. And the optimized drag value is this value. Okay, this is an optimized drag. If you remember, the baseline value is about 2.0 E minus 2. And you will also print out the converged angle of attack. Converged, this is the converged angle of attack, is this value. It's much lower than the, I think it's 5 point some degrees in the baseline design. You can use a very low angle of attack because you will create some camber to generate the lift. And then the optimized shape variables, optimized constraints, all the constraints should be satisfied. All right, that's how you read this log file. Any questions for the log file? Okay, let me see what's next. Okay, so I assume that, that you are now familiar with this log file, and that's what's next. Where you can look at some other things, such as the design variable history.txt. It will print out the history of your design variable, evolution of your design variables for all iterations. So you can see that first iteration, second iteration. And also, if you look at this total derivatives history files, you can get sensitivities for all the iterations. Okay. And also, just recently, we added a new capability that allows you to output a DAFoam FFD that could be very useful for post-processing. This flag is here. I'm going to show you where is it. It's in the run script. If you say write DAFoam FFD to true, default value is false, you will get some DAFoam FFDs. You can load them along with your optimized shape. I'm going to show you how to do that. And I'm going to show you my I was plotting this. I'm going to delete this because I'm not going to use that. Okay, let's go back to this plot I showed you before, and I'm going to look at from this. Say this is your optimized design. So you can also load your optimized FFD points. It should be called this DAFoam FFD underscore 018 in the optimization folder. Everything will be written to the optimization folder. I'm going to load this file. And let's see what happened. Here we go. Well, actually, it should be called for some reason 0017 instead of 18. I have a typo here. Once you load this, you will set up this attack profile. Hit OK, hit apply. It will show up here. You might want to show the wireframes, something like this. Zoom in, you can see that FFD point also changed. They can visualize it. All right.
Is it possible to change the place and the number of FFD points?
What do you mean by place and numbers?
Can we add more FFD points, for example?
Oh, yes, you can. But once you hit the wrong button, you cannot change anything anymore. But you can obviously you can increase the number of FFD points. that will be done later when I talk about how to change the configuration. Yes, the answer is, short answer is yes. How about we talk about that later? Okay,
Okay.
sounds good. Yes, in this case, we use about 20 FFT points, very close, but you can increase that. All right, that's a new capability. And what else? Oh, details of configuration files. Well, so now let's look at, now we know how to run the case, we know how to visualize the result, we know how to read log files. What's next is that the details of the configuration files. So I do want to spend some time to talk about that, because I will not assume that you are very familiar with OpenFOAM. And a lot of the configuration file is just pure OpenFOAM configurations. Let's talk about those. So first of all, I want to show you the list of files and folders in the, before you run the optimization is this. After you run optimization, a lot of new files are generated. Let's talk about what are they. Okay, so before you run optimizations, you can see the 0, the orange is essentially the initial and boundary conditions. If you are familiar with OpenFOAM, constant and system, 0, constant, system, these folders, these 3 folders are the OpenFOAM essential. Okay, with these 3 folders, you can run OpenFOAM. The rest of the folders you need that because you want to run DAFoam. Okay, so this includes the FFD folder and the Airfoil profile, and the run script to clean out everything, and run script to generate mesh, and this is a dummy file for Paraville. And pre-processing script, if you remember, you run this script, and the run script of Py, this is the main Python script we need to prescribe to control everything. So, but after the optimization is done, and you generate, you see you can see that a lot of new files are generated. That includes 0.001 all the way to 0.00, actually should be 17. These are the flow solutions, flow field for each optimization iteration. Because in this case, we get about 17 iterations. That's why we see these files. Okay, so that's why when you load it in Paraville, you can hit run and it will show you the evolution of all the optimization. Okay, these are the flow solutions. These are the O file, O file, O file. And this is a new DAFoam FFD. You can have from 000 all the way to 018. So the DAFoam FFD, and this file, DRDW coloring, is the output from the coloring solver, which will be used in computing the preconditional. You don't have to touch that. And DV constraint of that. This is the visualization of constraints. Very easy to visualize. I will show you an example later. And design variable history, all the history of the design variables, and also history of your total derivatives. I already showed you that. And this is the old file. This is new file that is generated that saved the log file for the mesh generation. And this log OBT is the full log file I just showed you in the past few slides. And this file, I want to spend some time to talk about objective function history. And sometimes I get some confusion that this is not the objective function for the entire optimization history. Instead, it's the objective function for the one flow simulation. This will be used mostly for unsteady flow. Now, for the steady flow, you really don't need to look at this. And this is a log file we just checked. It's O file, O file, O file. These are all the O files. So you can see that you can expect some new file that is generated. Okay. Now let's look at the next. Let's check the file and folders one by one. Let's assume that you are not very familiar with OpenFOAM. So in the 0 folder, let me see if I can go to the 0 folder. You can see some files here. And this is the OpenFOAM essential folder that will basically ask you to provide the initial and boundary condition for all the variables. In this case, because we are using a same model, we really need these 4 files. Okay. So let's just open one of them. Let's say we open the U velocity file. What do we need to define in this file? So we look at a U. Well, so you can see that we need to define the internal field initial condition. We also need to define the boundary conditions. And you only need to prescribe the correct boundary types. You don't actually need to prescribe the correct boundary condition values, because these values will be overwritten anyway in the run script. We're going to use that. But you do need to prescribe the correct boundary type. For example, the symmetric plan is a symmetric boundary condition. The far field should be inlet, outlet. The wing surface should have a non-slip boundary condition, which means the velocity should be 0. Okay, that's just an example. All the rest of the file will be very similar to this velocity. Okay. Then we will have another velocity that's in this 00018 folder. That's the optimized velocity. This is the baseline velocity I just showed you. It's uniform. But let's look at the optimization converged. Let's see what's the U velocity. This is a zip file. You can vi u.z gz. You can see that. Well, now this time the internal field, the volume mesh, the velocity at the volume mesh will no longer be uniform. Of course, that's expected, right? So this is converged flow field. If you go back to the bottom, you can see some converged flow field at the far field. That's the converged flow field. You can, of course, visualize them in the preview, but if you really want to check some numbers, you can also open that. Okay, that's the that is the 00118 folder. Okay, in this folder, and currently in this folder, okay, there is an additional folder called polymesh. So what's inside this? Oh, by the way, let me go back to this slide. So in this 0.0018 folder, we have a polymesh. Let's see what's in the polymesh. It saves the deformed mesh point coordinates for the converged, for the optimized design. You can see that it has 8,000 points. Their coordinates are here. These coordinates will be different from your baseline design. Just keep that in mind. Okay, now so let's finish this. Let's go back to the constant folder. Constant folder is another folder that's needed by OpenFOAM. It saves some flow properties, turbulence models, mesh information. So if you go to the constant folder, so this is polymesh. It has some mesh information, including the number of cells, number of points, owner and neighbors. These are all the mesh informations. For example, if you open this boundary file, let's open this boundary file. You can see that, okay, it has the definition of the boundaries, how many faces to have, the start faces, which number is definition for all the boundary faces, okay? Let's move on to next. And this transport property files is also in the constant folder. It has the molecular viscosity for the flow, and also you can define the turbulence model in this turbulence properties here. The default model is spotlight armorers. That's the constant folder.
I would like to ask you a question. Like here, if we want to run an inviscid solution, so do we need to make it 0, like new?
Well, unfortunately we don't support an inviscid simulation, but I think if you set it to 0 and you set the turbulence model, this spotlight armorers to dummy, and then turn off the turbulence model and set it to 0, you should be able to reproduce an inviscid simulations, I think. I'm not 100% sure because we assume that flow is always viscous.
All right, like what you said, like what we have to do with the RS model, like if we put new equals to 0 and RS model remains same, or we need to write something else over here?
Yes, you need to replace this spotlight. Can you see my highlight part in the PDF? Here.
Yeah.
You need to replace this with dummy, D-U-M-M-Y.
D-U-M-M-Y, dummy.
Yes, that's a dummy turbulence model. Basically, it's a laminar model. It will not add any turbulence viscosity in the flow.
All right, all right.
All right, hopefully that this will reproduce the inviscid simulations. You need to check that out. We have not gotten a chance to check that, but this should give you the inviscid flow. All right, so let's move on to the system folder. And the system folder has a lot of control parameters for the flow. I do want to mention them very briefly. Let's go to the system folder and the control dict that defines the system parameters, such as how many steps you want to run for the flow. In this case, we want to for 1,000 steps. How frequent do you want to save the flow? We only usually save the last step. We don't need to save any intermediate steps. And all the parameters are here. One thing that is kind of different from OpenFOAM is that we switch off anything that is output to the screen by OpenFOAM. We control the screen output completely in DAFoam. Okay. Another folder is called decomposed part of dict. That's also in the system folder that control the how many number of CPU cores you want to use by default is 4. By the way, you don't need to change this file. This file will be automatically generated by DAFoam when the optimization runs. Okay. And another folder is called FV schemes. This is a folder that defines the discretization schemes. We have some pre-set up for incompressible flow case, for compressible flow case, for subsonic, transonic. They are all in the tutorials. Make sure we have tested those setup, it worked well. So we strongly recommend keep those set up. Don't change the things in the FV scheme for a particular case. Okay, very similarly, we have this FV solution file that contains the strategy for solving linear equations. Again, the setup we use is the best we found so far, including the under relaxation. For most of the case, as long as you are running the same flow solver, then probably you don't need to change those. All right, so we have already talked about by 50 minutes. I suggest we again take about 10 minutes breaks, and then we come back in 10 minutes and continue the third sections, continue and finish this configuration files. Thank you. All right, welcome back. This is the third section of this workshop. Before we talk about some of the configuration files, let's finish the rest of them in this section. Okay, so we talk about the basic configuration files for OpenFOAM. Now let's talk about some specific file that is for DAFoam optimization. So the main scripts you need to run to generate a mesh is this preprocessing.sh. So I guess you already run this file to generate the mesh, but inside, let me open my terminal here. So let's clear this up. If you look at this preprocessing, if you look at this preprocessing, it has a couple of lines. I'm going to explain each line. What do they mean? The first line is run a Python command to call this script to generate the mesh, and we use the PyHip, as I mentioned, to generate a very high quality structural mesh. If you open this file, let's open this file, this gen Airfoil file. You can see that there is user input sections that control the mesh density. And the first few lines, you need to prescribe where is your profile. And this profile needs to be, you can see the instruction flow should be separated. The upper and lower surface, they should be separated. And the mesh coordinates should be from the leading edge to the trailing edge. And we should truncate the leading edge, trailing edge to get blunt. We don't support the sharp trailing edge. Z-span, N-span is the Z-span is what's the width in the Z direction, span-wise direction. You can give actually any values. N-span is usually we set at 2 points because it's symmetric. It's a 2D case. But the PS parameter, PS means pressure side, which is essentially the lower surface. And you need to prescribe the first DX from the leading edge. What does it mean? Like we're going to open my paraview here to illustrate that. For some reason, I cannot. Let me just show like this. Yeah, I can just. I really want to minimize this way, but I can't. I'm going to highlight this. I'm going to highlight the mesh. I'm going to check this. I'm going to go back to the baseline design. So DX1 is the mesh size near the leading edge for the lower surface here. This is DX1 PS. Alpha 1 means the expansion ratio along the stringwise directions is 1.1. So which means the ratio between this mesh size and this mesh size is 1.1. And also, very similarly, DX2 PS means that the pressures are lower surface. What's the mesh size here? Near the trailing edge. Okay, and then with the expansion ratio 1.1 along this direction. Then DX max PS means the pressure side, what's the maximal mesh size, probably somewhere here. Okay, the mesh size in the x direction, by the way. And very similarly, we can do the same mesh size for the suction side, which is the upper surface. Okay, so another parameter we want to control is the number of points at a trailing edge, MPTE, this parameter, equals to 5. If you go to here, which means that we have 5 points, 1, 2, 3, 4, 5 for the trailing edge. Okay, this is what does this do. And this MP extrude 33 means that we extrude 33 points in this direction, in the vertical direction, and this direction, from here, from the wing surface all the way to the far field. In this direction, we extrude 33 points. Okay, this is what does this parameter mean. White wall means the mesh size for the first cell near the wall is the mesh size in the vertical direction from here to here. That's the white wall. Okay, and March distance 20 means that the distance between your wall, your airfoil surface to the far field, which means the distance between somewhere here to here is 20. Okay, this is our parameters you want to control in this script. Once you prescribe these parameters, you just run the script, it should be able to generate a mesh. But the problem is that the mesh that is generated is not in the OpenFOAM format. Essentially, the rest of the commands, if you look at the pre-processing, the rest of the commands, these commands essentially convert the mesh that is generated by this PyHip to the OpenFOAM format. Okay, so I will not read all of this. I think the slides has a lot of details in terms of how do we convert. We first convert to the Pro3D format in OpenFOAM, split the patch. And there's one thing I do want to mention is the auto patch, because when you run this command, you will basically convert the mesh that was just generated by the PyHip to the OpenFOAM format. And then what will happen is that OpenFOAM mesh does not know how many patches you have, how many boundaries you have. It will only have one boundary. So that's why you need to run this command to automatically split the boundary, such that you can separate what's the symmetric plane, what's the far field, what's the wing surface by a feature angle of 16 degrees. Okay. Then after this, you will generate a bunch of new patches. They will have names such as auto 0 all the way to auto 4. They don't mean anything. That's why in the last command line, we need to basically group some patches together and rename them to some meaningful names, such as wing, in, out, symmetric, such as such. Anyway, the rest of this script basically converts the PyHip mesh to the OpenFOAM mesh. Any questions for that?
Yes, I have a question. Well, is there any parameter to control the
Well, it seems that I'm losing you.
Cells, growth ratio of the cells. Is there any the growth ratio?
It seems that I'm losing you. Can you say a question again? I guess you're asking about growth ratio.
Exactly.
Yes, the growth ratio is automatically determined in the, let me show you a log file. If you look at the log mesh generation, this log file is generated by PyHip. What's the best way to? So if you go to this file, you can see the growth ratio here at things in the last column, the march distance and the growth ratio. So it's around 1.3. It's not very good because it's a very, very coarse mesh. Okay. This is the growth ratio. It should be in the log mesh generation.txt. That makes sense?
All right.
All right. Sounds good. That's the growth ratio. And well,
and sorry.
One.
Yes, go ahead, Usman. Sorry.
All right. One more thing. I would like make crawl to main. Like I would like to make the region after trailing edge more
So it seems that Lucy, I can't hear your question very well.
As compared to the region like in front of the leading edge.
Okay,
all right,
so
I'm just typing it.
yeah, maybe you should, yeah, try to, maybe, yeah, let's try to type in. I see your question about a mesh, general mesh, a density box. Okay, well, right now, PyHip does not support that. At least DAFoam does not support that. If you want some refined mesh to capture the weight, you have to use unstructured mesh. The short answer is no. PyHip does not support that. At least does not support that for DAFoam. Does that answer your question? All right.
Maybe can I just add one thing? But with the pre-processing, because what I've been doing so far is using my own mesh, and I've bypassed this step just by using the native block mesh. So just wanted to mention that just in case others may want to use their own mesh and may want to bypass this pre-processing step.
Oh, yes. So I guess your question is that you can always bypass. Yes, you can bypass this step. You don't have to run this if you already generate your mesh. Thank you. Thank you for the comment. All right, so let's assume that we already generated the mesh. And then, by the way, one thing I want to mention is that the airfoil profile needs to be separated, and the coordinates should be from 0 to 1, but you need to truncate the last few points to make it start from what, like 0 to 0.999, something like that. We don't support sharp trailing edge. So there are some comments in the slides you can read, and I'm not going to talk about those. So because the next topic is that FFD points. Well, so in this case, we are going to use a script to generate FFD. If you remember, we already load FFD here. If you zoom in to the paraview set, this is the optimized FFD, right? So this is the optimized FFD. How do we generate this FFD points is through this script. So if you go to the FFD folder, and if you open the gen FFD, this scripts, and then you should be able to generate FFD. It's very straightforward to use this, but its capability is very, very basic. You can generate only a box, rectangular box, and you can prescribe how many points in the X direction, how many points in the Y direction, how many points in the Z directions. And let me, I guess I have a plot here. So we have 5.1, 2, 3, 4, 5 points in X directions, 2 points in the Z direction, 2 points in the Y direction, 2 points in the Z directions. That's why you need to prescribe this. You also need to prescribe the corner points, the coordinates. So the corner point, for example, the corner 0, 0, this is the corner point, I think, this point. And then the second point should be the corner point, this point. And you have 8 corner points, this point, this point, this point, this point, and similarly for this 4 points. Once you define the corner points for the box, and then this script will automatically add some interior points in the X, Y, and Z directions. So keep in mind that FFD point have to completely contain the design surface. If the design surface is outside of the FFD point, you will get some errors, at least some warnings. And this is definitely not good. Okay, another thing I want to mention is that usually for wing or airfoil aerodynamic shear obturation, we only set up 2 points in the vertical directions. We don't need to set the third point in the middle. That's not quite necessary. And sometimes it might cause some issues. So in the vertical direction, we only set up 2 points. In this case, because we are running a 2D case, in the Z direction, span-wise direction, only use 2 points. But for 3D case, you might need to set up more points in the Z directions. Any question for the FFD point generation?
Yes, I have one. What type of function do you use to interpolate the shape between 2 FFG points?
Well, we just make it uniform. So right now we don't, this, as I mentioned, this is a very basic script. And we assume that once you define these 8 corner points, we are going to uniformly insert some points in between. So if you want to generate more complicated FFD points, you probably have to use some commercial software such as iSync or maybe PointWise, something like that.
Thank you.
I also have a question. Actually, I have two questions. The first
Go ahead,
question
please.
is this Python script that uses blocks. Like, would I be free to simply define points in space completely freely without the Python script?
Yes, you can. If you want to write each point by hand, yes, that you can definitely do that. But keep in mind, it needs to be in the Plot3D format.
Yeah, okay, I have to think about it. But anyway, second question would be, you said that it's important that the geometry is completely enclosed. Now, I don't find it to be very uncommon just to optimize a part of a shape. Like for whatever reason, you want to keep, I don't know, the last half of the airfoil, you want to keep it constant, but you want to change shape of the frontmost. Or another example would eventually be you want to optimize the wing of an aircraft, but not the fuselage. Like if my geometry is not contained inside this box, will it stay constant?
No. So there's one thing I want to mention, that when I say the geometry has to be completely within the reserve point, I mean only your design surface. For example, if you are taking the wing body configuration, they have wing, you have a fuselage, you can separate the wing and fuselage as different geometry in OpenFOAM, right? They have different patch names at least. And then you can set the wing as the design surface. You need to generate only a wing box, FFD box that only contain a wing itself. You don't have to cover the fuselage. But for some reason, if your wing and fuselage are in the same patch, then you have to generate a FFD point that contain both of them. Otherwise, it will be very, very wrong. So essentially, what will happen is that those geometry that is outside of the wing box or FFD box will be snapped towards the FFD box. Your geometry will completely screw.
Okay, so given the fact that for whatever reason, I want to optimize only the frontmost 50% of the airfoil, I would define basically 4 patches, like the rear, the aft end, and the front end. Like I would separate my mesh into front and back, and then enclose only the front part, and then it will run smoothly.
That's right. So that's one way to do it. Another way to do it, you can look at this example that you can still generate use one patch, but you can say, I only allow these 2 points to move. For example, this points to move, but the rest of the point cannot move. We have a mechanism to allow that. No FFD point can move. You can say only some of them can move, some of them will keep fixed. What will happen is that the rest of the geometry that is in a region that FFD points don't move, then they will not change. For example, if you say, I only allow you to move these 8 points, 1, 2, 3, 4, 1, 2, 3, 4, okay? The geometry somewhere here will not be moved. If you give more FFD points in the X directions, you can have more direct control. You don't have to separate the surface geometry all the time. You can still choose which FFD point to move.
Okay, cool. Thanks.
All right. Thank you. I got another question. The chat says that how to set out the control points for a curved tube. Well, again, this script only generates box FFD points. I guess for your application, you probably need to use iSim or some other commercial software to do that. So you can generate those. You can think of these FFD points, they are structural mesh, they are volume mesh. Okay, so you can generate some structural mesh, convert them to the Plot3D format. And there is not a very easy way you can generate such, curved tube using this script. No, the short answer is no. Hopefully that answers your question. Thank you. All right.
I have 2 questions. First is it possible to create more than one block? Because if we have several parallel channels for optimization. And the second question is, it is possible to create FFD point for conjugate heat transfer because we have both solid domain and the flow domain.
Okay, that's a very good question.
Problem, how do we create the FFD points?
Okay, that's a very good question. Let me show you something. I'm gonna, hopefully you can see this. And I'm going to go to, hopefully you can see my web browser, and I'm going to go to tutorials. And we do have an example that can show you how to create 2 FFD blocks. So it's in this DPW4 aircraft case. If you go to this case, if you go to the FFD, generate FFD, you can see that we can create 2 blocks. So, and the number of points in the X direction for the first block, for the second block, number of points in the Y direction for the first block and second block. You can use this grid. Essentially, it will generate a one single Prof2D file, but has 2 blocks. Then you can select which block to control and which points move in which block. So I suggest you to take a look at this example that has actually has multi-block FFD generation. And in regarding your second questions, if you have multiple domains like flow domains and solid domains, the short answer is no, we cannot do that. We do not support conjugate heat transfer at this moment, but we can extend for that. And the way we do it, that I guess you will need to share the same FFD points that you can apply to both geometry. But short answer is that we don't support this capability at this moment.
Okay, thank you.
All right, thank you. Any more questions for the FFD points? All right, so it looks like we have a very good discussion here, and which also means that I need to go a little bit faster for these slides. Finally, we are at this run script of Pi. That's the most important scripts, and we need to look at, and that's why I want to put it at last. But let me set out some correct line number. So if you open this run script, as I mentioned, this script control everything. You need to set up all the parameters. You need to set up parameters for all the components in this framework, in the MACH-Aero Framework, that includes your optimizer parameters, DAFoam parameters, OpenFOAM parameters, mesh deformation parameters, and the FFD parameters. It has, let me see how many lines, 200 lines, it's not too bad. In the first section is input parameters. You can choose which task to run. And OBT, if you look at this, the default optimizer is IPOP. You can switch to SLSQP, just change this keyword. And also the default task is to just run optimization, but later on you will see that you can also choose to just say, I just want to run the flow solver, just set it to run primal, or I just want to run the adjoint to get ingredients. I don't want to do optimization. You can just set the task to run adjoint. Of course, you can verify the sensitivity. So there are a few other tasks, but today we are going to talk about optimization, this task. That's the default task. Okay, so let me go back to the very beginning of this script. In the first section is the so-called input parameters. Basically, you define your boundary conditions. So what's the far field velocity here? Pressures, because we are running an incompressible flow case, the pressure is related to the reference pressure. That's why it's 0. It looks strange, but it's relative pressure. And it's turbulence variables, other turbulence variables for the other turbulence models, the target lift, initial angle of attack. A0 is the reference area to normalize the lift and drag. Okay, after that, we go into the section called DA options. So these are the options for DAFoam. So first of all, for example, we need to define what is the design surface. This name should show on any your OpenFOAM mesh. So if you don't have a mesh called, if you don't have a patch name called wing, it will get an error. Also, which solver do you choose? We use different solver for different flight conditions. And this is the Jacobian-free capability we recently implemented that it will give you machine precision, accurate adjoints. And this primal minimum residual is the residual tolerance for flow simulation. The next key is the boundary condition. If you set up the primal PC, means that it will override whatever boundary condition you define in your OpenFOAM file. For example, 0/U. If you prescribe some boundary condition there, and you also prescribe here, this will override the OpenFOAM one. Just keep it in mind. Next, you are going to define objective functions CD and CL. And well, this is just an example. If you look at the DAFoam documentation website, it has a lot more detailed explanation. What do you mean? what do we mean by this? For example, here I put some description here. And for example, I want to define an objective function, the name, you can give any name, that just call it CD. And it can have multiple parts, meaning that you can say, I have wind and fuselage, okay? I want to compute drag for both of them. So the part one could be the drag on the wing surface. The part two could be the drag on the fuselage surface. Then you can give them different weights for this drag by setting up scales, okay? So another example is that you can create the total pressure between the inlet and outlet. The part one is inlet, the part two is outlet. And you give the scale for inlet 1.0, you give the scale for outlet minus 1.0. Then the pressure, this objective function, what becomes the inlet pressure minus the outlet, something like a pressure loss. That's a convenient way to set up. But for this case, I only have one part. And the type is force. The source is patch to face. What does that mean? It means that I will collect the patch names you give it to me to compute the drag. And you need to prescribe what are the patches. Just wing, right? I want to compute the drag on the wing surface. And because it's a drag, because it's a force, it has some directions. You need to decide which direction you project to. In this case, you can prescribe this keyword, so parallel to the flow, and alpha name is alpha. So it will look for the alpha design variable you prescribed and automatically find the flow direction and project this force to the flow direction. The scale is just a scale. You normalize the force. I normalize the force to the CD. Add to algebra means that if you set it to force, it will only print CD to the screen while you solve the flow. You will not solve the algebra for CD. You will not compute the gradients for CD. Then you cannot set it as a design or as the objective function or constraint function. But default value is I will set it to true. Very similar setup for CL. Any question for the objective function setup?
Yes, I have one. I don't really understand here. You are minimizing CD and maximizing CL. Oh no, what do you have? Like, why is there both?
Okay, so we are going to constrain CL. We are going to set a lower bound and upper bound. Both of the bounds are 0.5. Essentially, it will become equality constraint. That's why you need to compute. You could set it as object function. Well, the name itself is a little bit confusion that in the sense that it actually is objective and constraint function.
Okay, that's clear. Thank you.
All right. Thanks. After that, we need to set up some adjoint options. And most of the time, you don't have to change that. And also, we need to normalize the states. We need to normalize to state to make the adjoint converge faster. For incompressible flow case, we need to use the dynamic pressure. For other variables, just use the far-field variable normalized. And this is the final difference step size. Most of the time, you don't have to change that. The adjoint PC lab, what does it mean? It means that we will not recompute the preconditionals, which is very expensive to compute, and until we are at 100 step. And essentially, we will not recompute it at all. We are just going to compute it for the baseline design, reuse it for all the rest of the iterations. And you need to provide the empty flag here to save the design variables. And this is a flag I just explained before that. We will output the default FFD during optimization. The default value is false. After the DA options, we need to set up. DA options are for the DAFoam only. Okay, I get another question. I want to answer that. Is it possible that, that's a question about FFD. Is it possible that two different FFD blocks overlap? We strongly recommend don't overlap two FFD blocks. So because that will create some, well, if you overlap a little bit, that should be fine. So what the bottom line is that the FFD points blocks could be slightly overlap, but make sure that the geometry, your design surface geometry does not belong to two different FFD blocks, because that will impact how this geometry is snapped to the FFD points. That might create some confusion. Your FFD point blocks may be slightly overlap, that's fine. But just again, make sure that your geometry does not belong to two of the FFD points. Does that answer your question? All right, I hope yes. All right, let's move on to this. Let's continue to look at run script of pi. So we just talked about DA option, that's for DAFoam. Now we have mesh option. This is for IDOP. Well, the only thing you need to set up is the symmetric plane. You need to give the point origin and point normal. Because we have two symmetric planes, you have to set us two symmetric planes for this. And the next option is for the optimizers. If the optimizer is SNOpt, we are going to use this set of options. If the optimizer is IPOpt, you are going to use this set of options. Well, so I'm not going to go over what do this means, but the most common thing you need to change is the max number of optimization iteration you want to run, and the optimality tolerance and constraint tolerance. Okay, so if you can check the PyOSparse website for more details of what does each of this. Let me go back to each of this optimizer option mean. Now let's go to the.
May I ask a question?
Sure.
So for the maximum number of iterations, let's say you have a case where you have after the 20th iteration, you have set it to run for 50. But let's say after the 20th iteration, it has stabilized thereabout, or up to a certain point, it has stabilized. Where would you need to change in order for it to stop without having to go through the whole 50 once it has reached a point where the objective function is no longer changing? Okay,
that's a very common scenario. That the short answer is that if your optimality drops below your tolerance, the optimization will automatically stop. As you probably saw in this case, in this tutorial, it will stop automatically at 17 iteration. Although we say we allow you to run for maximum of 50, so it will automatically stop. But a lot of cases that maybe your tolerance for your optimality will not drop to -6, then we just manually stop it. You can monitor your job, your objective function are not really changing anything, but your optimality is still not -6. You can just manually kill it.
Okay. I see. Well, I'm asking this question because in running a simulation, I think it was for 50 iterations, and after the 20th, at the 20th, the drag had a certain value, and then towards to the 51st thereabout, the drag was continued to be the same value. So it still continued doing the calculations, even though there is no change in the drag in the constraint, sorry, in the objective function. Is there a way to avoid that, where it would automatically stop?
The short answer is no, there's no way you'll automatically stop, but I can probably, I guess what will happen is it's very likely that it's because you are using the old version of DAFoam. If you use a latest version, if you set up this option, I'm going to go directly to that option. This one, the adjoint Jacobin set it to Jacobin free. I would expect all the Airfoil cases should converge to -6 for the optimality. It will automatically stop. The reason you saw that behavior is because, let me go to it, is because the default option used the finite difference method to compute the Jacobians, which is not very accurate, which means that the adjoint gradient is not very accurate, like 0.1% accurate. Then a lot of times at the very end, very near to the end, that you cannot find the correct gradients, you cannot improve the objective function.
Okay. Okay, understand. Okay, thank you for the answer.
Set to the new option, hopefully you will be able to converge more tightly. All right.
Okay, thanks.
Thank you for bringing this up. And this is the optimization setup. Okay, let's continue to look at the design variable setup. That's a very important one, I guess. And the first section, we just define a function to change alpha, change the angle of attack. This function will be called in PyOSparse by the flow solution, and which is essentially open form flow solution. It receives two inputs, variables, your design variable value. It can be a value, it can be a list, and the geometry. Okay, you can change this value to change the geometry, but because this is an angle of attack, we're not going to change this geometry. We're going to just leave it there. We'll not use it, but we will change we will use the value. So we are going to say that we're going to select the first value from this list and this is the angle of attack in degree. Then we need to convert it to in radians, and then compute the velocity components, UVW, and set this velocity component. If you look at this, set this velocity components to this DAFoam options primer PC. Primer PC is what we have defined here before primer PC. Before default, you have a default value, but after that, after calling this alpha function, you should be able to update your velocity component based on the angle of attack, and then you set it to the DAFoam, update the options. Okay, you need to define the options to do that. And then after that, we can load our FFD points here. So in the FFD folder and add a reference axis. Remember to always add a reference axis, although sometimes you don't need them. So I will still recommend you add a reference axis. I'm going to explain when do we need to use this reference axis for 3D case. Now you need to select points. That's referred to the question before. Can we just select some of the points? Yes. So this script basically said I volume. What does that mean? It's also related to the multiple blocks. I volume 0 means that we are going to select the first FFD block. If it has 2 blocks, you may select the second block by setting I volume equals 1. But because we have only 1 block, we are going to select this block, and we're going to select points. So you can see these comments here. So we are going to select all the points from this block and allow it to move. Okay, then we select this point, we add this in here. Well, let me use this to explain because my font size is a bit large. So we select the first FFD blocks and select all the points in this block and give to this variable, say DVGO add geometry design variable, local variables, which means all the points can move. Give a name, we call it shape Y, give a lower bound and upper bound from -1 to 1. It can move in the y-axis in the vertical directions. It has a scale 1, and the point set select is the point we just generate. PS equals to this. We select all the points. But what if we want to select some of the points? You can just say I select 1 to 2, maybe 1, 2, something like that. And then you will select only part of that points. The rest of the point will not be able to move at all. So this is the way you select some points to move. Any questions for selecting FFD points? All right, very good. I guess that's very clear that you just say, I want to allow all these points to move. And then also after that, you need to update the DI options to say that I have a shape Y variables, which should be consistent with this name. And then this has a type of FFD. All the shape variable, their types will be FFD. And the second type of variable, we will remember this code is slightly different. It's called add GVGO local, global. And this one before is local. Local means that we allow FFD points to move. The global means that we either want to move a set of the points together, or you want to just change some angle of attack, for example, global variables. And then we give a name alpha, and give an initial value alpha 0, give a function. How do we compute the alpha? How do we apply this alpha to the boundary condition? That's the function we just defined as here. Also give a lower and upper bounds, give a scale, okay? Of course, after that, we need to update the DA options for this alpha. This is just the options for DVGO. This is the geometry engine. We also need to update the DA options for alpha. The type is angle of attack AOA, and we need to give it a patch. Where do you apply this far field boundary condition when you get a new angle of attack? It's in out. And you also need to give the flow axis and the normal axis, because if you look at this, our flow axis obviously is the x-axis, flow is in this direction, and the normal axis is y direction, okay? This is needed because we need to know how do we compute the flow direction. Okay, oh, it seems that I got 2 more questions from the chats. Can we specify varying FFD moving directions along the objects? I mean, control point, yes. Well, for example, you want to allow this FFD point move not only in the y direction, also in the x direction. You can just add one more line, something like this. I'm going to show you. If you want to move also in the, where is it? Here, this line. I'm going to copy this line. You are going to say, I'm going to add a new set of I'm going to select the same points. Don't want the line number. I will call it shape X. And you will move in the X direction. That's it. So you just call this function twice. You add the same points, but for the first variable, you only allow it to move in Y. The other case, you only allow it to move in the X direction. Okay, hopefully that will answer your questions. Okay, now I'm going to go back. I'm going to undo this because I don't want to change this script. And after that, okay, any more questions for the design variable setup? Oh, if no more question, I'm going to move on to the next section. Let's see. Oh, this is the DAFoN initialization. You don't need to change this part. Next, constraints. Okay, we do need to spend some time to talk about constraint because most of the common question is how do we set our leading and trailing edge lists? So first of all, I want to mention that the reason we want to add a constraint, this is geometry constraint, is because we want to mimic the structure constraints. Otherwise, if you don't set a constraint, this optimization will give you a very thin airfoil to minimize drag, which is definitely not what we want. That's why we want to impose a constraint that say the volume cannot drop. So you can only increase. Also, the thickness cannot drop to its maybe 50% of its initial thickness. That's the overall constraint we want to add. But how do we add it? So first, we need to define a so-called leading and trailing edge list, AE list and TE list. And for this simple case, this list can just a straight line. You need to define 2 points. Okay, the first point coordinate is this. The second point coordinate is this. This is the leading edge list. These 2 points basically define this red line. The trailing edge list also has 2 points. These 2 points define the blue line here. Okay. Remember, this trailing edge and leading edge list needs to be completely within your design surface. You cannot be outside. I will explain why. So once you define this leading trailing edge list, and then we just add the volume constraint and thickness constraints. Okay. So, okay, to add a volume constraint, we add this core. We give a leading edge and trailing list, number of spans, number of core points. You need to generate to sample the entire airfoil. I am going to explain that later in lower and upper bounds for the volumes. Scaled equals true, which means that this lower and upper bound are based on the relative volume instead of absolute value for the volume. Okay, so 1.0 means that the initial volume, 3.0 means 3.0 times your initial volume. Which essentially says that if the volume cannot decrease, it can only increase. Okay, now what's this number of span and number of chord? Okay, 2 and 10, how do we explain this? Well, so remember that we have defined this leading edge points, leading edge list and trailing edge. Let's assume these are the leading edge and trailing edge list points for this airfoil. After you define this, we will create a 2D mesh. Okay, so then the number of chords 10, which means that we will add 10 points between the leading edge and trailing edge. 1, 2, 3, 4, 5. We will add 10 points in between. And then we will add 2 points in the span-wise directions. In this case, if you look at this, span-wise direction is this directions, okay? We only need 2 points. We don't need more points because in the span-wise direction, the geometry has no variation. But for 3D case, in the span-wise direction, you do need to add some points. The rule of thumb is that, let me go back to the slides here. The rule of thumb is that the number of core points and number of span points should be very similar to the number of FFD points in that direction, because in the X direction, we have 10 FFD points. That's why we say n chords equals 10. Then you will create 10 points in these directions. And for each point, you will project up and down, and then project the points to your wing surface or the airfoil surface. You get this point and this point. Okay. After that, you can see that we essentially create some trapezoid volumes that is approximation of the entire airfoil volume. So our volume will not be based on the airfoil geometry. Instead, we are going to base on this project points, these black points. Okay. Once you know the coordinate of all these black points, we can compute our approximate volumes. That's how we impose the volume constraints. So any questions for the volume constraints? Okay, very good. So I'm glad that this is clear. And also for the thickness constraint, very similarly, when you project up and down, and this line is thickness, right? This line is thickness. Remember, thickness is local thickness, which means that if you create 2 by 10 points to project, you have 20 thickness constraint. Again, the thickness constraints is relative. So point A means 80% of your initial thickness. 3.0 means 300% of your initial thickness. Okay, that's the, and for more details, you can check the MACH-Aero website. They have a more detailed explanation of all these constraints added. All right, so next constraint is so-called linear constraints. Essentially, you want to link the displacement of the F50 points. Why is that? Because this is a 2D case. We don't want this airfoil, we want the airfoil to be symmetric in the Z direction. That's why we add this linear constraint. Basically, we link the displacement between this point and this point. If this point moves up by 0.1 meters, and this point should move up by 0.1 meter. This is done by calling this add linear constraint functions, and have some explanation here. I think this graph should explain how does it work. If not, you can load this file, this dv constraint.dat file, which is in plot 3D, a type plot format. You can visualize the linking between F50 points. Also, we need to link the leading edge because we don't want the leading edge to change. So we link, say, this point, if this point moves up by 0.1 meters, this point be moved down by 0.1 meter. This is done by this command. Any question for this linear constraints?
I just want to I have a question for the thickness constraint. Sorry, I didn't ask it in time, but I'm just wondering because looking at I'm using an older version of DAFoam, and in that version there's a upper and lower bound for the thickness constraint. And in this version that I'm seeing, I don't see that lower and upper bound.
It's right here.
Ah, it's there. Ah, okay. Ah, okay. Okay, I was looking at the other one. Okay, thanks.
All right.
Thank you.
All right. That's very good. And it's there. That's very good. All right, let's continue. And by the way, more questions? Okay, if no more questions, let's move on to the next section. Actually, that's almost it. And the rest of it, once you set the constraints, this section initializing this OPT function, you don't have to touch. And this, you really don't need to touch a lot. Just a few points you want to look at is, one is this. And you basically, this is solve CL, okay? Oops. We recently add this, and you will create an object for the pile spots objects, add variable, add constraints, also add the design variable, add a objective function CD. This name should be consistent with the name you define in the object function in DA options. Give a scale 1, and you can also add some physical constraint, for example, CL constraints here. As I got a question before, how do you add inequality constraints is here. So you add a constraint, CL is constraint, and lower bound, upper bound, they're the same, which essentially means that it's equality constraint. Okay. Sometimes there's a trick that sometimes we always want to minimize drag, but what if you want to increase the drag? Just set the scale equals -1. Then you will increase the drag. But by default, you will decrease your object function. And that's it. That's the rest of it. And the rest of the script is just some other task we are not going to talk about. So that covers most of the scripts I think we need to cover. Any questions so far for the round script of Pi? All right, very good. So one thing I do want to mention is that I got a question about, well, you define the CD and CL as an objective function. Is it possible we do a CD, CL over CD? So leave to drag ratio as an objective function. How do we do that? So it's not a straightforward way to do that. You have to manually write something, which is in this function. If you look at the source code of DAFoN/DAFoN OPT functions.py, it defines the function called calculate objective function values. Okay, so this function is given to the optimizers here. It's given here. you need to provide a function that can compute an objective function, okay? So very similarly, you need to provide a function to compute the constraints, other the sensitivities, the gradients, it's here. Let's first look at the objective function, this function. You will receive xdv is your design variables. It will return your functions. This function will be a key, will be a dictionary. If you have CD, you will have a CD equals this, CL equals this. It will also return a fail flag. If the flow simulation fails, it will return fail flag, and then give it to let the optimizer know that the simulation failed. So essentially what does this script do is that it will run the DAFoam functions, OpenFOAM functions to compute, run the flows, to return you the dictionary that has all the objective function values. So if you want to set CD over CL as an object function, you have to modify the script to say your functions add a new key, maybe say CD over CL equals CD divided by CL, something like that. Okay, very similarly, you need some treatments in this another function, calculate the objective function sensitivity to manipulate the sensitivity. So you can see that the algorithm is solved here. Okay, I'm not going to spend a lot of time because this is about how do you develop new capability in DAFoam. Again, in this workshop, we focus on how to use DAFoam. Okay, so we cover most of the case. Now we go to our last objective. How do you change configuration file for a new case? Okay, we probably need to go a bit over 3 hours. I hope that's fine for you. And now we are done with this. I'm going to go through some very common modification needs. For example, how do you change the flight conditions? Well, very straightforward. Just let me open this file. So just change the boundary condition here. So if you want to run it at a higher speed, just change it to like, for example, 60 meters per second. So it should be very straightforward. And then next question is, how do you use more mesh? Well, obviously you need to change this generate airfoil mesh.py this file. As I mentioned, these parameters include the mesh size. You need to reduce the mesh size if you want to increase the mesh density, okay? And again, I'm not going to talk about details. I believe I already talked about those in the previous slides. Then another question is, how do you change the different turbulence model? Well, you can change this file, constant turbulence properties. By default, it's turbulence Armaras models. You can change it to K omega SST. I think we support maybe 7 to 8 turbulence model. If this model, you set it dummy, then it means that laminar model, you will not have any turbulence model at all. Okay. How to use more FFT points? As I just mentioned, just increase this. So if you want to use 10 points in the X directions, go to this directory, generate this, run this file, and you should be able to, generate more FFT points. Just change this to 10. Okay. So I do want to mention, I forgot to mention that how do we load FFT points? Well, I have some notes here, I think. Well, hopefully I didn't miss that. Because ParaView have some issues loading the plot3d file, you have to convert to the tagplot format to load it in ParaView. Here we go. Oh, I missed. I guess I missed it should be somewhere in these slides, and then I can't find it. But if you check the slides, and there is a script that you can use to convert plot3d into tagplot format and then load it in ParaView. Okay, don't directly load the plot3d format because your ParaView will crash. Okay, that's how you increase the FFT points. And then how do you optimize a different airfoil? There are a couple of steps you need to follow. First, you need to, of course, provide the new airfoil profiles. Remember to separate upper and lower surface. Remember to truncate the last few points to make a blunt trailing edge. Okay, and also you change this gen airfoil mesh.py script to link to the correct new airfoil profiles. Otherwise, you will still use the Naga 12 as the default. The next thing is that you need to change the FFT points because your airfoil change, that you make sure that your FFT points still contain your full entire airfoil geometry. And then after that, run this command to clean out the previous runs and then run the new optimizations in Docker using this command. How do we use a different solver? For by default, so if you look at the case I provide, and we have a couple of folders, this is for incompressible flow, we are going to use the DA simple form. But if your flight condition is subsonic, you have to use the DA rho simple form, which includes the density in the flow in the governing equations. If it's transonic, we have to use a solver called DA rho simple C form. So let's first talk about the subsonic case. Well, the setup is very, very similar. Let's go to the subsonic case. The only difference is the run script. You can see that, well, we add some new variables. For example, the pressure is no longer 0. We have to use the absolute pressure. We need to set the temperature and such and such. We have some new variables, and the solver names, you need to change it to rho, to DA rho simple form, because this is the solver for subsonic case. And then a very important thing is that you need to copy and paste these keys to the to this solver, because these will bound your variables to make sure the flow solution is stable. The default open form solver, it does not perform very well in solving subsonic case. Then we have to bound them. This is the new implication for the rho simple form. And also some other notes you can read from here, but those things are very minor. Now let's move on to the transonic case. Well, it's very similar to subsonic, except that, let's go to the transonic case. Transonic case. And if you look at a transonic case, the velocity is at a transonic speed is 200 meters per second. That's one main difference. And then also, of course, you need to change the solver name, that the C here means consistent. Essentially use the simple C algorithm instead of a simple algorithm to solve the flow. Well, another main difference is that you might need to add this transonic preconditional options, set it to 1, such that you will converge well for transonic condition. Of course, the FE schemes, FE solutions for subsonic and transonic, they will be very different from the incompressible flow case. Again, in the tutorial, we provide some setup. We believe that's the best for the cases. All right, so let's see. Any questions?
Yes,
Right.
I have a question. What is the omega that it comes in all the solvers? The omega.
Yeah, it's a turbulence variable for K omega S
okay.
variable. Yes.
Okay.
If you don't use K omega S as turbulence model, you don't have to set this up.
Okay. All right. Thank you.
All right. All right. If no more question, let's see how do we use more CPU cores. This command, very straightforward. All the rest of it will be automatically tackled. You don't have to change that. But remember, run this all clean before you run a new job. So, okay, the last topic I want to cover is very briefly is how to run a wing aerodynamic optimization. So if you know how to run an airfoil aerodynamic optimization, extending to wing should be very, very straightforward. And here's the case setup. If you want to look at this, you go to the folders I provide. And before we were in this Nakadawa 12 folder, you can go to Oniha M6. And this has the setup for the wing case. You can see overall, they look very, very similar. You have FFD folders, you have a run script, you have general mesh script, you have pre-processing scripts, such as such. Here's a summary of this case. In this 3D case, the main difference is that we use more FFD points. And well, the volume and thickness constraint is slightly different, and it's at a subsonic condition. Although the case on the M6 is at transonic condition, but I just want to provide a case that runs in a very coarse mesh. Here's the FFD points. You can see that, well, you can still use the general mesh S pi to generate this FFD, but if you want more body fit FFD points, you probably have to use the ISIN. But we have 1, 2, 3, 4, 5, 6 layers of FFD points in a span-wise direction, and 10 points on top and 10 points on the bottom in the string-wise direction. So the process running is exact same as the 2D case. Just run this generate mesh, run this for optimization. Okay, so a couple of difference in this pre-processing scripts. So let me open this pre-processing case. Well, you can see that it's slightly different in the sense that this is a 3D case. Okay, we are going to still use the pi heap to generate the mesh, but the pi heap requires a surface mesh, which should be in the structure format. So that's why in this case, we just download this surface structure mesh from that side. Okay, download from there and extract it. We don't have an automatic way to generate structure mesh, which means you probably, as mentioned here, use some commercial software to generate structure mesh, surface mesh. Once the structure surface mesh is generated, we just run the scripts. Sometimes we need to coarsen it because the surface mesh is very refined. We want to coarse it such that you can run it on your laptop. Then you run this script to generate the volume mesh, very similar to this script is very similar to the 2D case. I'm not gonna explain. And actually the rest of the steps are almost the exact same as before. Okay. So we basically convert the Pro 3D mesh to OpenFOAM format. Okay, that's the pre-processing. So another main difference is in the run script. I do want to spend some time to talk about this. If you look at the run scripts, for the 3D case, the global parameters section are the same, the DA option are almost the same. And if you go to the design variable setup, there's one difference. I'm going to put it here. Let me don't wrap by. Okay. So we add a reference axis, so body axis, and we say add X fraction point to find 25% of your core wise, which is the reference axis, essentially this blue line. Okay. What does it do is that later on we can define some twist variables that will twist the wing section with respect to this reference axis at this 6 span wise location. So this is very easy to set up. Just prescribe, I want to have a reference axis that's aligned with your FFT points. It is at 20% of your core wise directions. And the out, by the way, align is ZK because it's along the Z axis, this reference axis. And then it will return the number of twists, basically number of FFT points in the span wise direction in this case. In this case, it should be 6 points. Okay. Now that's basically what this slide says. Next difference is that in addition to defining alpha angle of attack, we also define a twist variable. In this case, twist variables has the very similar function form as the alpha variables. You receive this variable value as the inputs. It's a list that has the twist at all the 6 span-wise directions, and you will apply some change to the geometry object. You can see that we loop over all the twist span-wise directions and change and rotate the reference axis by this degree. By how much degree depends on the values in your design variable. This will be the input from the optimizers. They run this function to actually change the geometry. Keep in mind that in this case, we don't change the root twist. That's why you have some I-1 this index here. The angle of attack setup is exact same as 2D case. So of course, once the shape variables the same as before, the alpha variables the same as before, but we also need to add a twist variable we just defined, right? So we just add the twist variables, the initial values are all zeros, okay? Meaning that it's the initial twist. Then give a function to compute the twist, which we already defined here, give a lower and upper bounds. Remember, this -10 is in degree, okay? Once we get the twist variables, and very similarly for the constraints, we need to set up the volume and thickness constraint. But for the 3D case, again, we need to provide the leading trailing edge. You can see that it's very, very similar to the 2D case, except that this line needs to be like kind of parallel to your leading edge and trailing edge, but within the wing. You need to define 2 points. This leading LE lace, these 2 points, okay, basically define this red line. The trailing edge lace, these 2 points, basically define these 2 lines. This blue line, they are within the wing. After that, you can call this add volume constraint, add thickness constraint to add the constraints. If you look at this, now I use a number of span points 10, number of core points 10, because it's no longer 2. It was 2 in the Airfoil case, but it's 10 in this case because we have about 6 points in the span-wise direction. We need to set up maybe about 10 points, sample points to better approximate the volume and thickness of this airfoil. And the leading and trailing edge constraints are very straightforward, just 2 cores. We fix the leading and trailing edge, meaning that when you change the shape, you will not change the leading and trailing edge. But of course, you can rotate, then you can rotate the leading and trailing edge. Any questions for this constraint setup? If not, there are some minor changes, such as I got a question in the very beginning that if you have some mesh quality that's not very good, can we relax it? Yes, then here is an example. How do we relax? You need to define this in the options. You can see that this option called check mesh threshold, and you can relax this maximum non-orthogonality to 75 or make max skewness to 10. You can relax this option. I mean this rest. All right, this is the last slide. I want to provide you some useful link for OpenFOAM, for DAFoam documentation, also for the MACH-Aero documentation. In the MACH-Aero documentation, it has more details in terms of how do you set up the constraint and design variables. All right, thank you very much. That's all for today's workshop. And let me